My name is Noah Corbett, and I'm going to be presenting on predicting state switches in chaotic dynamical systems. So what we're going to do is we're going to take a chaotic system, a very famous one, the Lorentz attractor, and we're going to project it down onto a two-dimensional space. The reason we're going to do this is because in a lot of applied research, we tend to not know information about every single state variable that influences the system. So by foregoing knowledge of the z variable, we're going to try to make predictions in the Lorentz attractor accordingly. So what we notice is that a trajectory on the attractor tends to make loops about one of the equilibrium points, and it does so seemingly randomly. If we look here, we can model the amount of loops that an orbit will make before it switches states onto the other side of the attractor. And it seems to be modeled closely by a geometric distribution. That would mean that it's almost completely random and very difficult to make predictions in this setting. So what we do is we're going to leverage the fact that the minimum distance that a trajectory makes before switching states seems to be highly correlated to the number of loops that the trajectory made. And so what we're going to do is we're going to create a Poincare-like section that we're going to call the distinguishing line. What we're going to do is we're going to see where each trajectory intersects the distinguishing line and see if we can leverage this to make predictions about future state switches of the system. What we notice right away is that there is some seeming threshold that we've labeled in blue that we're going to call the critical distance that completely determines whether a trajectory is going to switch states in its immediate next step. If the trajectory has a crossing distance of less than the critical distance, then it's going to make a loop again, and if not, it's going to switch states in its immediate next state. We can look over in the results section that the immediate next state will be predicted accurately 99% of the time with this test sample of 496 points. Now, how do I predict multiple state switches in the future? Well, we're going to do so using what's called a Gaussian process. So to predict the next state, I need to predict the next crossing distance with my distinguishing line. And to do this, we have a Verhulst diagram that shows a Gaussian process of how I can model future crossing distances. Once I know the future crossing distance, then I'm going to predict the next state by using the same critical distance as before. With that in mind, we notice that the number of predictions that I can make correctly until my first error is about 6.47 on average, which is exceedingly better than the optimal random guessing procedure of just guessing the highest probability move in the next state. So why are we doing any of this? Well, a lot of chaotic systems in the real world require knowledge, perfect knowledge of all the variables that are influencing the system. However, in a lot of cases like animal movement, where certain metabolic processes of the animal themselves influence the future states of the system, that would be infeasible. But with this method, we're actually going to be able to make accurate predictions of macroscopic features without knowing all the variables. Thank you.